morning, everybody. Today, my video is going to be about this 8 by 8 by 8 LED cube, which I put together a little while ago, but I've been sort of lazy about doing a video on it, mainly because there's so much coding involved in it. Coding is not as fun as hardware, but basically, there's plenty of videos out there about creating an 8 by 8 by 8 LED cube. So if you want to know the details on the construction of it, it's fairly straightforward, just a lot of soldering. Basically, an 8 by 8 by 8 LED cube is a tour de force in construction because 8 by 8 by 8 is 512 LEDs. And that's a lot of LEDs, and these are arranged in common cathode configuration. What does that mean? Every LED has a positive and a negative, an anode and a cathode, right? So all of the cathodes are arranged in layers, and so they're connected by as a layer. So all of these cathodes are basically wired together. Now the anodes, the positive sides, are all connected together in columns. And so all of these columns are basically individual, the anodes from the LEDs are all connected together. And so these are all made using an LED, using the LED cube jig, which is basically, I took a piece of plywood and I just measured out 64 holes, plugged the LEDs in, and made it a lot easier to construct the thing with the soldering. So in any case, all the positive anodes per column are connected together, and all of the negatives are wired together as an entire layer. So every one of the negative sides of each LED is an individual layer. Now I sort of hid it here, but if you look closer, this little wire right here is wired underneath and controls the first layer. This one right here is the second layer, third layer, fourth layer, etc., until you reach the final layer, which is right here connected. And so I made it out of the same wire, so you can't really see them. And the circuit is as described previously in other videos. It's basically, I did it all on a breadboard. It looks like a little bit of a mess, but each layer is controlled by a shift register. These are H74HC595s, and each layer and all its associated LEDs are connected. Here's the resistors for each LED column. Each one of these wires is a separate column. So there's 8 shift registers by 8 columns in each. And basically, this is all controlled by a Raspberry Pi. Now, a lot of videos on YouTube with regard to the LED cube are all controlled by Arduinos. And I didn't have an Arduino, nor did I want to start programming in the C++ language for the Arduino, and I'd much rather program in Python. And so these are all controlled by 3 separate pins on the Raspberry Pi, and that's all you need. The blue one here is for the data. The gray one, or the black one, is the clock, and the gray one is the latch. And so these are all connected to the first shift register, and then all are cross connected. The only addition to the circuit that I did make is on the clock. Since the clock is so fragile and easily triggered by just static electricity and me getting near the wire, I put a differentiator circuit on it, basically a 0.01 microfarad capacitor and a resistor linked to ground. And so it sort of differentiates the clock signal. It makes it a lot more recognizable and more difficult for me to trigger it by just being near it. So they're all the power and ground rails you can see here. All the yellow wires are cross-connected clock, the white wires are cross-connected latch, and the blue wires are the serial data. So the way the shift registers work is you shift serial data into them and they output in parallel, so to each individual one of these. Now, the 8 layers are basically connected via this last shift register, 2 LED drivers, which are 2N2222 transistors. I doubled them up so they wouldn't get too hot. And basically, the base of the transistor is connected to the output of the shift register. So it basically turns on a layer based on whether there's a 1 or a 0 being output from this shift register. And so in order to allow complete control of the circuit and allow for multiplexing, this last shift register in the code is basically set to cycle a 1 from pin 0 to pin 7 repeatedly in order to turn on and off each layer individually. And this does this really fast in order to allow for an adequate multiplexing. Otherwise, you get ghosting you get LEDs that light up when you don't necessarily want them to. So I have this set up as in code that's written in Python from this Raspberry Pi, and I have this set up as basically an audio responsive LED cube that gets a music signal from this microphone, which I've used in previous videos. The microphone signal gets read as raw data in the Raspberry Pi, and like most using the pyaudio library, you can get the microphone data. Then using the NumPy library, you basically can make an 8 by 8 by 8 array of 1s and 0s based on an FFT calculation algorithm for different frequencies. And doing this all in software is a lot easier than doing it in hardware, even though it requires a lot of trial and error in coding. So to summarize the code, I have multiple different things here, but basically you assign the pins, the data pin, the clock pin, and the latch pin. You import NumPy and pyaudio. I have my FFT library in a separate program that I made before. But basically the way the program works, the way the code works is first you initiate everything. So you set your GPIOs, you define them as outputs for the clock, latch, and data pins separately. Then I defined an array of points, which is a 8 by 8 by 8 array. And I initiated it all to 0s using NumPy. And then the way the central portion of the algorithm works is you basically clock in all the data. So I have several different test programs that I used for this, but in essence, I have a function that I've defined here called set points, which basically is a giant for loop that sets all the points based on what the values are in the array. And the values in the array get changed up based on the FFT algorithm. So once all the points are defined and in the array, it's a multi-dimensional 3x3 a three-dimensional array essentially of 8 points. And so what I do at the end is I flatten the points and make it a one-dimensional array of all 500 or all 64 points per column, or all 512 points, and then I have a function that renders the points. The render function is fairly straightforward. The render function just basically does the main GPIO output, which is basically you set the clock and latch to 0, then you input all the data. There's a for loop that runs through all the points and runs through the data, and then at the end of it, it latches it all in. And it does this repeatedly because this function is called on all the time, the rendering function. And so from that point, you can make all sorts of different functions. You could create cubes, all by just basically manipulating the data that you want in the array of ones and zeros. And this can create multiple animations. You can make text out of it. You can make a spectrum visualizer, audio spectrum visualizer. You can make boxes that go back and forth. So all of these different functions I have separately defined, and in the main program, what I do is I have a frame count. I start at a frame count of 0, and every time there's like a certain number of frames done, what happens is we get the values from the FFT algorithm for each of the 8 individual frequency spectrum areas, and then I just mess with them in different ways in order to create a usable data and fill up the 8x8x8 array, and then that gets rendered into the cube. So the basic program is, and each and every several 100 frames, I guess every 100 frames I've defined it here as, it changes into a different animation for that. And so hopefully this explains it to some degree. And then at the end of the program, if you stop the loop, it basically cleans up the LEDs, and I have a function that clears all the LEDs in the cube. It turns them all off by turning them all to 0 using the same render function. So in any case, let's give this a shot and see how it goes. So I have here music that I'm going to play from my usual source, which is royalty-free music on YouTube via an iPad. And let's get that started. All right, music started. LED's off at the moment, but the microphone is on. So let's get this started. And let's go. So that is the LED cube. Let me turn it off. And when you turn it off, when you stop the program, it just clears all the LEDs. And so that makes it a lot easier for the cleanup and everything. There's no errant currents. By the way, the power to this entire thing, I have it wired to the breadboard here. So basically, I had to fit it all on 2 breadboards, but it basically comes from this old block from a Apple iPad. When a lot of these LEDs are on, their current draw is fairly high, and so you need a separate power supply. You don't want to power it from the Raspberry Pi because that's going to potentially fry it. There's like several, there's potentially almost an amp of current that flies through here. If you use a smaller block, there's a chance that you might overwhelm the current and it just will turn off on you. But for the most part, it's basically based on everybody else's construction design, the common cathode design. Each of these layers basically cycles very quickly. I have it as a set at 1 kilohertz. So 1,000 times a second it goes through the 8 layers of the transistors here to turn it off and on the layers. The transistors, the way they work is basically since these are common cathode layers, so each of these layers is basically connected to ground when the transistor base is turned on. So when the shift register sends a 1 to this first transistor, for instance, the signal goes to the base of the transistor, which turns it on and basically grounds that layer. And so whatever anodes whatever LEDs are on in that layer at that time will turn on for a very, very short period of time. And when you cycle through it over and over and over again, you get an effect where it's called persistence of vision. So an LED will appear to be on to the human eye, even though it's being turned off while all the other layers are going on. And this is to prevent different, if you only want one LED in a column to be lit, instead of all of them, you turn on that column, and you don't turn on the column when it goes to the second layer, because it's in the array, that column has a 0 in it in the second layer, and so on and so forth. And that way, when it cycles through very quickly, only this one appears to be on and this one will appear to be off, even though this one is on very briefly when that layer is grounded. So in any case, that is my explanation. Let me know if you want more explanation or a better one, or a schematic, or access to the code. Let me know in the comments if I get more than 5 people who actually watch this video. I'll be impressed. But the reason I did this is I was looking through for Raspberry Pi controlled LED cubes, and really there's nothing out there. Everybody's been using Arduinos, and as much as I want to get started with the Arduino, I don't really feel like learning C++ to do the Arduino sketches. And I know a lot of people have already written programs for it, but it's more fun to write your own. So in any case, this is the LED cube. At some point, I'm going to hide all the wires inside and put a front and back and a switch on it. But for my next project, it's most likely going to be an audio spectrum visualizer using the LED cube. But I'm going to use analog circuitry and cut out the Raspberry Pi and all the coding completely. Kind of what I did with the amp, only I'm going to create 8 different frequency spectrum bands in each of these columns, and I'm going to have them go from back to front in terms of magnitude of each frequency. And I think that's going to make it a lot smoother looking and less code dependent and more analog dependent, which is going to be prettier, I think. So in any case, thanks for watching, and happy Saturday.